And we're going to record now. We're going to go back to here. Now, here are sensory neurons. This is a cell body. And these fine probes made out of glass and connected to voltmeters can measure the uh, path of action potentials and record an action potential. Remember, an action potential is a signal that goes from negative to positive very quickly and then goes back to negative. That's because sodium is coming in and potassium is going out. So when sodium goes into the neuron, it becomes very positive. When potassium leaves the neuron returns to its negative charge. Okay, so let's look here. Okay, launch the interactive. Okay, let's play this. Okay, so we can keep going here. So a very sharp microelectrode is inserted into a sensory neuron here. So this is an action potential. So underneath the microscope, a very sharp microelectrode is inserted into a nerve cell body. The electrical activity is viewed with, as time proceeds, a half a second, you have these uh, synaptic biochemical is released and it causes positive sodium to flow in. Now, these right here are called subthreshold potentials. Only when the movement of enough sodium into the cell does an action potential occur. So you can see it's about half a second and it's about 100 millivolts. The inside of the nerve is negative, minus 70 millivolts. So as neurotransmitter biochemicals cause more and more sodium to enter the nerve, when it reaches a threshold, it takes off and forms an action potential. This moves down the nerve, okay? So let's keep going. Okay, so this is a plesia. This is a sea slug. You can grow their neurons in a culture dish. So an electron is placed in the sensory neuron, both to monitor its activity and to stimulate the cell by injecting electrical current. So these are two neurons from a plesia, which is a sea slug, and they're able to isolate these nerves and grow them in a petri dish. So again, this is the cell body. This is the cell body of the sensory neuron. This is a microelectrode that records and can stimulate this sensory neuron. So if we keep going, now we have, as I said, if you have uh, sodium flowing into a nerve because of the opening of channels, if the change in voltage is below threshold, then you don't have an action potential. So if the voltage becomes more positive, if it's strong enough, you're going to have this action potential, which happens very quickly. You'll see how that happens in a moment. Okay, so let's look at that again. First stimulation is subthreshold. Sodium has come into to a nerve, and the amount of sodium coming in where the sodium channels are opened by the neurotransmitter, then this is subthreshold. Okay, notice here's another stimulation that's also subthreshold. Remember, as you go from bottom to top, the inside of the cell is becoming more positive. So to generate an action potential or an electrical signal, you have to have the positive change be enough to generate the action potential. Notice how quickly that occurred. It's a very rapid change. Okay, so here we're going to record from two cells into the motor neuron. So here's electrode 1. Electrode 2 is not very clear, but uh, electrode is inserted into the motor neuron that receives information from at the synapse. Uh, the electrical activity between the two cells can be viewed simultaneously and compared. So there's another, here's the electrode right in front of me. So the electrode here is measuring the changes in voltage when the sensory neuron has a synapse with this uh, second neuron, a motor neuron. Okay, so the electrode will show you when there's no nerve activity, it will remain flat. This is the trace in the sensory neuron when it's depolarizing or becoming more positive as the image is recorded. This image is on an oscilloscope, like a little TV. So these electrodes are attached to these neurons, and this oscilloscope can measure uh, very, very rapid changes in how the nerves change their voltage. So this is the motor neuron. This is the sensory neuron. Okay, those are all sub-threshold stimuli. Let's watch that again. So the amount of sodium that rushes in has to cause a positive change, okay? So when the sensory neuron fires an action potential, a voltage change called a synaptic potential is seen in the motor neuron. If it's not sufficient, this single synaptic potential, if it's too small a change, it will not generate an action potential. So let's see what that looks like. There you go. So you can see how when this change in voltage is high enough, it generates an action potential. Let's watch that again. There you go. And this action potential occurred because this synaptic potential in the motor neuron was strong enough. Okay, so if we keep looking, if we have synaptic potentials, they can build or piggyback on one another. So if they come with sufficient frequency that they are caused when these changes are very close together, these synaptic potentials can add up and cause an action potential. So one synaptic potential is not sufficient, but multiple potentials can piggyback on one another. When this happens, you get sufficient change in the neuron, and once threshold is reached, you have this very rapid change in potential, and that's an action potential. Okay, I want to stop recording for a moment.